Now phase 4 and phase 1 are going to correspond with diastole. Phase 2 and phase 3 are going to correspond with systole. Okay, so phase 4 and 1 in that order is diastole, whereas phase 2 and 3 is systole. Okay, now we're going to talk about the pressure. We're going to really zone in and talk about how the pressure is changing in the atria and the ventricle through each of these cycles, right? Through each of these phases. So in phase 1, what valves are open? What's happening in phase 1? What valves are open? The AV valves, right? So in phase 1, we have blood moving from the atria to the ventricle, and the AV valves are open, right? So as blood spills into the ventricle, the pressure in the atria is gradually rising, right? It's gradually rising. And that is to maintain the pressure gradient so that blood can continually move from the atria down to the ventricle, okay? And as we mentioned before, at the end of phase 1, the atria is going to start to gently contract just so that it gets all the blood out down into the ventricle. Okay, so we have atrial pressure slowly rising in phase 1. Ventricular pressure is going to be low. Why? Why do we need to keep ventricular pressure low here? To maintain what? The gradient, the pressure gradient. We cannot have ventricular pressure higher than atrial pressure because that will close the AV valve and we will not be filling the chamber. Okay? Let's see phase 2. In phase 2, what valves are open? What valves are open in phase 2? Think about it. So phase 2 is what? Isovolumetric ventricular contraction. So what valves are open in that phase? None, right? So neither of the valves are open in phase 2, right? But what chamber is sort of raising its pressure? What chamber is gradually increasing its pressure? To the ventricles. So the pressure in the ventricles is gradually increasing in phase 2 in an attempt to overcome the pressure in the vessel to open the semilunar valves. So ventricular pressure is going to be raising in phase 2. Atrial pressure is now going to fall. Okay? We do not need that gradient anymore. The AV valves are closed here. Phase 3. So what's happening in phase 3? What's happening in phase 3? We have, I'm not hearing. Right, so the semilunar valves open, nice. So the semilunar valves open, blood is being squeezed out of the ventricle into the vessel, right? And so as blood leaves the chamber, what is the pressure in that chamber like? It's decreasing. So as blood leaves the ventricle and moves into the vessel, the pressure gradually decreases, okay? The pressure gradually decreases. The pressure in the atria is going to continue to fall until we start phase 1 again. So the atrial pressure doesn't fluctuate very much. The only time it rises is at the end of phase 1, which is the end of systole, which trying to get that last volume of blood out into the chamber. The ventricular pressure is going to be low in phase 1, gradually rising in phase 2, and very high in phase 3, and then it drops again in phase 4. So this is your atrial and ventricular pressure. Now, because the AV valves are open, the pressure in the atria and the ventricle is going to be the same, right? Both chambers are communicating here. When the AV valves close here, right, these chambers are no longer communicating. So the atrial pressure stays low, but the ventricular pressure rises. When we have the ejection phase here, we're squeezing blood out of the ventricle, so pressure is rising, and then that pressure is going to gradually fall as you relax the ventricle. Okay? Now let's talk about the pressure in the aorta. Right? The aorta is that main vessel that leaves the heart. It's going to pump blood all throughout the body organs and tissues, and we're gonna look at the pressure between the ventricle and the aorta. Any questions so far? Okay, so during diastole, what valves are open? What valves are open in diastole? AV, right? So during diastole, the AV valves are open, right? The ventricles are filling, they're relaxing, blood is moving from the atria down to the chamber. But if we look at the semilunar valves, they're closed, right? Why are the semilunar valves closed? Why are the semilunar valves closed in diastole? Because we don't have that pressure gradient. We don't have pressure in the ventricle high enough to open those semilunar valves. Okay, so because of this change, the aortic valves remain closed. So blood is going to be leaving the aorta, moving throughout the rest of the body, and it's going to drop the pressure in the actual vessel. The AV valves are closed. Blood is no longer moving through the the semilunar valves are closed. Blood is no longer moving through the semilunar valve, and so the pressure in the vessel decreases. As that pressure decreases, it's going to get to its lowest point, and that is called diastolic pressure, right? Diastolic pressure. And that's an important number in measuring your blood pressure. That's the bottom number. That's the lowest the pressure in your vessels can get. This is because the valve that feeds this vessel is now closed, and so the pressure drops until it gets to its lowest, which is diastolic pressure. During systole, these valves open, and as these valves open, blood is being rushed from the ventricle into the aorta. The pressure is going to rise. When it gets to its highest pressure here, that is your systolic pressure. Okay, and that's how you get your blood pressure. Systolic over diastolic. So the maximum pressure in the vessels over the minimum pressure in the vessels. Okay. Now let's talk about mean arterial pressure. So mean arterial pressure is the average aortic pressure throughout the cardiac cycle. So if you took the aorta and you measure the pressure in it, the average pressure is your mean arterial pressure. And that number or that measurement is going to denote how much driving force, how much pressure, how much force is blood moving throughout your body with, right? How much energy or force is the best way to put it, is the blood leaving your heart and being pumped throughout your body. So that's an important number in determining cardiac function. Okay. Now, as blood leaves the ventricle and moves into the aorta, we want to remember that the aorta is an elastic vessel. What does elastic mean? It can stretch. So the aorta is an elastic, stretchy vessel. So when blood enters the aorta, it's going to stretch, right? It's going to stretch out. And that stretching is going to allow it to store energy, right? It's going to store energy. And the energy that it's storing is to maintain a continuous pressure of perfusing the body. I'll explain this a little bit. So basically, if the semilunar valves close, one would be tempted to think that, okay, there is a interruption in the amount of pressure with which the body is being perfused. That is not true, okay? Even though the semilunar valves close, the amount of pressure that we are perfusing the body with remains the same. Why? Because when the valve is open, the vessel stretches. It stores some energy. When the valve closes, the vessel is going to recoil or constrict on itself, and that is going to generate some new pressure, which is going to maintain continuous perfusion. Okay? So the aortic pressure is going to be maintained throughout the entire cardiac cycle. Let's look at this image here. So during systole, right, the aortic valves are open and blood is flowing through into the aorta very nicely, right? Now, this vessel is going to start to expand here. And that expansion is storing up of some energy, some energy to generate pressure, right? Now, during diastole, when this valve closes, the vessel is going to then recoil or constrict on itself. And the recoiling of that vessel is going to generate some additional pressure to maintain perfusion throughout the body. So at no time during the cardiac cycle is the amount of perfusion, the amount of pressure that we have blood flowing through the body interrupted. At no time is that perfusion interrupted because of this mechanism. All right, let's look at this question here. All right, so does the heart spend more time in diastole or in systole? Diastole, right? Diastole. Can anyone say why? Why did it spend more time relaxing? Right, so you want to give some adequate time for the blood to fill that ventricle, right? You also want to allow for the muscle to physically relax, okay? Any questions so far? So this is diastole. All right, so what we're going to talk about now is some ventricular volumes. Okay, so this is where we're going to get into some math here. Okay, so the ventricular volumes are going to change based upon when that ventricle is emptying versus when it is filling. Okay, so we have a volume called end diastolic volume. An end diastolic volume is what blood is left in the chamber, or what blood is in the chamber when the entire diastole is finished. So how much blood did the chamber actually receive from the atria? Okay, that's your end diastolic volume. How much blood was filled into the heart to be pumped out? Okay, when do we measure end diastolic volume? What phase would we measure that? What would be the best phase to measure end diastolic volume? Come on. Phase 2, right? Phase 2 would be the best phase to measure that. Why? Right, so it just got squeezed from the atria into the ventricle. We now close the AV valves. Nothing is moving. The volume is not changing here. So this is all the blood that the ventricle was able to fill from the atria before it has a chance to squeeze that out or to contract. Okay, so phase 2 is the best time to measure the EDV or end diastolic volume. Let's look at the end systolic volume, right? The end systolic volume. This is the amount of blood that's left over in the chamber after we've pumped the blood out, after we've squeezed it out. So all of that blood is not ejected. There's some left there. Okay, when would be the best time to measure end systolic volume? When would be the best phase to measure your end systolic volume? Right, phase 4, right? So phase 4 is when, again, we've closed the semilunar valves now, we're done ejecting, we're done squeezing blood out. And so what's left back in that chamber is what we want to measure. What is left over after systole, after the ejection phase? Okay, so phase 2 will give us EDV, phase 4 will give us ESV, okay? Now, stroke volume is the amount of blood that has actually been ejected. The amount of blood that has actually been ejected. Okay, how much blood was actually pumped into that, that vessel? And that is going to be your end diastolic volume, which is all the blood you filled, minus your end systolic volume, which is what's left after you've ejected. All right, I'll say that again. Your stroke volume, how much you pumped out into that vessel, is going to be your end diastolic volume, right? All the blood that you filled into that ventricle, minus your end systolic volume. What is left in that chamber after you have ejected the blood? Okay, so end diastolic volume minus end systolic volume gives you your stroke volume. How much blood did you actually send out into the vasculature? That's your stroke volume, okay? Now, typically, EDV is 130 milliliters, right? ESV is about 60, that's what's left in the chamber after systole. And so your typical stroke volume is about 70 milliliters or so, okay? All right. Then we get to ejection fraction. And things get a little bit more complicated here. So the ejection fraction is what percentage of that end diastolic volume did you actually eject? All right, so what percentage of the amount of blood that you filled into that ventricle completely, how much of that, what fraction, what percentage did you send out into the cardiac, into the systemic circulation? And that is your ejection fraction. So that's your stroke volume, how much blood you ejected out, divided by your end diastolic volume, how much blood you filled at the beginning, or at the end of diastole rather, okay? So your stroke volume, what was the amount of blood that you pushed out into the circulation, divided by your end diastolic volume, and that gives you your ejection fraction. Now, because we said stroke volume is usually 70 milliliters, and end diastolic volume is usually 130 milliliters, this is a fraction of about 0.4, which is about 54% at rest. So what does that number really mean in terms of cardiac function? What does that 54% mean? Who can rephrase that? What does that 54% mean? 54% of what is happening here? All right, so stroke volume divided by end diastolic volume, right? So 54% of the blood that you filled from the atria is being pumped out of the heart.